AI model for ISO 21001, a deep neural network, DNN, processes raw input data through multiple layers, transforming it using mathematical operations, maths branch, and feature extraction techniques, MASH's branch, to produce meaningful outputs. Here's a step-by-step breakdown. Pradeep K. Suri, author, researcher, consultant, and AI/ML architect. 1. Input raw data, MASH's branch. The raw data could be in different formats: numerical, textual, image, or time series data. Pre-processing, MASH's processing. Normalization/scaling, adjusting data to a common range, example min-max scaling, standardization. Feature engineering, extracting relevant features using statistical or domain-specific techniques. Encoding, converting categorical data into numerical form using techniques like one-hot encoding or word embeddings. 2. Mathematical transformations, maths branch. Once the pre-processed data is fed into the DNN, it undergoes multiple transformations. A. Weighting and summation, perceptron operation. Each input neuron is assigned a weight, and a bias is added. Z equals sigma, 11wi, plus bz equals \sum, x underscore I \dot w underscore I, plus bz equals sigma, 11wi, plus b. B. Activation function, nonlinearity. To introduce nonlinearity and allow the network to learn complex patterns, an activation function, example ReLU, sigmoid, 10, is applied. A equals f, z, A equals f, z, A equals f, z. ReLU, rectified linear unit f, z, equals max, 0 z, f, z, equals \max, 0, z, f, z, equals max, 0 z, common for hidden layers. Sigmoid, f, z, equals 11 plus e z f, z, equals \frac 1 1 plus e caret z f, z, equals 1 plus e z 1, used for binary classification. Softmax, used in multi-class classification. 3. Hidden layers, MASH plus maths combined. Multiple hidden layers extract high-level features by applying transformations layer by layer. Each layer's output becomes the input to the next. Mathematical concepts involved: matrix multiplications, linear transformations, gradient descent, optimization, backpropagation, weight updates using partial derivatives. 4. Output layer. The final layer produces an output using an activation function suited for the problem. Classification, softmax or sigmoid, probabilities for different classes. Regression, linear activation, predicts a continuous value. 5. Loss function and learning. The error, loss, between the predicted and actual output is calculated using a loss function, example mean squared error, cross entropy. Optimization algorithms, example ATOM, SGD, adjust the weights to minimize the loss through backpropagation. Conclusion. MASH's branch handles raw data processing, feature extraction, and transformation. Maths branch performs mathematical operations, optimizations, and backpropagation. The combination of data pre-processing and mathematical modeling enables the DNN to learn patterns and make predictions effectively. Python program for ISO 21001 in education sector using a neural network. The ISO 21001 standard focuses on educational organization management systems, EOMS, ensuring quality and effective learning experiences. A deep neural network, DNN, can be used to model and predict education sector outcomes like student performance, resource allocation, and institutional effectiveness. Neural network architecture for ISO 21001. Input layer, raw education data, example student scores, faculty qualifications, learning materials, feedback. Hidden layers, feature extraction, pattern learning, and optimization. Output layer, predicts educational quality metrics, example student success rates, institutional performance. Hidden layers contribution. Hidden layer functionality. Quality compliance layer evaluates compliance with ISO 21001 standards. Student performance layer predicts student learning outcomes based on inputs. Faculty development layer identifies areas for teacher training and improvements. Resource management layer optimizes allocation of learning materials and staff. Feedback analysis layer processes student and faculty feedback for improvements. Key insights. This model can predict and improve compliance with ISO 21001. Hidden layers extract insights from different aspects of education quality. Can be extended to include real-world datasets and deep learning techniques. ISO 21001, Multi-Factor Analysis, 3D Scatter Plot Explanation. Pradeep K. Suri, author, consultant, and AI/ML architect. Overview. This is a 3D scatter plot visualizing multi-factor analysis related to ISO 21001 compliance in education. The chart maps three critical factors. 1 X-axis, resource allocation, resource all. 2 Y-axis, student performance score, student score. 3 Z-axis, feedback score. Each point represents a data sample, categorized into needs improvement, blue points, students or faculty who do not fully meet compliance standards. Compliant, red points, those who meet ISO 21001 compliance standards. Bar chart interpretation. 1 Dense data distribution. The plot is densely packed, suggesting a wide range of student performance, resource allocation, and feedback scores. There is no clear separation between compliant and needs improvement students, indicating overlapping trends across different factors. 2 Balanced compliance levels. The red and blue points are mixed throughout the 3D space, showing that compliance does not solely depend on one factor. Some clusters of red points, compliant students, appear at higher feedback and resource allocation scores. 3 Key observations. Higher feedback scores and better resource allocation correlate with compliance, red points. Needs improvement cases, blue points, appear more frequent at lower student scores and resource allocation. Chart increasing insights for ISO 21001 compliance. Small blue diamond institutions should focus on improving resource allocation and faculty feedback mechanisms to enhance student performance. Small blue diamond, a multifactorial approach, balancing feedback, resources, and student engagement, is essential for compliance. Small blue diamond further clustering analysis could identify patterns in compliance and areas requiring intervention. Conclusion. This 3D visualization effectively demonstrates the interdependence of multiple factors in student performance under ISO 21001. While resource allocation and feedback contribute positively to compliance, further insights can be extracted by applying clustering techniques to identify key improvement areas. The video consists of 3 visualizations related to ISO 21001 compliance, each displaying different aspects of student performance, faculty quality, and their correlations. Below is a detailed explanation of each chart. 1 Histogram, Student Performance Compliance. Title. White heavy checkmark ISO 21001 Compliance, Student Performance. White heavy checkmark Pradeep K. Suri, author, consultant, and AI/ML architect. Chart description. X-axis, student performance scores, ranging from 50 to 100. Y-axis, count of students in each score range. Color coding, legend on the right. Blue, compliant students. Red, needs improvement students. The histogram is stacked, showing how many students fall into each compliance category for different performance score ranges. Insights. A significant number of students have performance scores between 70 to 90. The blue region, compliant students, dominates, indicating most students meet compliance standards. The red region, needs improvement students, is lower but still present, suggesting some students need attention. 2 Bar chart, Faculty Quality vs Student Performance. Title. White heavy checkmark Faculty Quality vs Student Performance. White heavy checkmark Pradeep K. Suri, author, consultant, and AI/ML architect. Chart description. X-axis, Faculty Quality Score, 1 to 9. Y-axis, student performance, sum of performance scores for each faculty quality level. Color coding, legend on the right. Blue, compliant students. Red, needs improvement students. This is a grouped bar chart, meaning each faculty quality level has two bars, one for compliant, one for needs improvement. Insights. As faculty quality score increases, the total student performance also increases. Faculty quality scores between 5 and 9 contribute to the highest student performance. Students categorized as compliant, blue, consistently have higher performance compared to needs improvement students, red. There is a noticeable performance gap between compliant and non-compliant students across all faculty quality levels. 3. Heat map, feature correlation in ISO 21001 compliance. Title: White heavy checkmark feature correlation in ISO 21001 compliance. White heavy checkmark Pradeep K. Suri, author, consultant, and AI/ML architect. Chart description. X-axis and Y-axis, different factors affecting ISO 21001 compliance. Student performance. Faculty quality. Resource allocation. Feedback score. Color coding, color bar on the right. Dark red, close to 1 high positive correlation. Dark blue, close to -1 high negative correlation. Lighter shades, lower correlation. Insights. Strong correlation observed. Student performance and faculty quality rightward arrow strong positive correlation, red. Resource allocation and feedback score rightward arrow also positively correlated. Weaker correlation. Faculty quality and resource allocation have less correlation, indicating they may be influenced by other factors. Overall summary. The histogram shows that most students are compliant, but some need improvement. The bar chart highlights how higher faculty quality positively impacts student performance. The heat map confirms that student performance is strongly correlated with faculty quality and other academic factors. The dark-themed visualizations provide clear insights into compliance and performance metrics, making it easier to identify strengths and areas for improvement in ISO 21001 education standards. Thank you.